Hello, everyone. Welcome to my talk about my research. First, I share my screen. So the title of my research is Decoupling for Smooth Surfaces in R3. This is a joint work with Jianhui Li, a PhD student at the University of Wisconsin-Madison. The outline for the talk is as follows. We first talk about the background of decoupling, and then we talk about the most important case, which is Bourgain-Demeter decoupling for the standard parabola. And then we move on to generalize the partitions of this according to each different phase functions and give a typical 2D result, which is part of my previous work. And then we move on to 3D to talk about a model case, and then we state our main theorem for this talk, and then we give us very brief sketch of the proof. So background of decoupling. What is decoupling? Decoupling can be very generally formulated. So let AI be a finite collection of disjoint geometric subsets of Rn. Here, by geometric, in most cases, it means the delta neighborhoods of some smooth manifolds in Rn. We will see in a moment what exactly these geometric subsets are. Given this geometric subsets and given two Lebesgue exponents P and Q, we denote by d sub pq of script A be the smallest constant, such that for any functions fi, which are test functions, each of them is Fourier. So each of it has Fourier transform supported in the AI. We have the following inequality. Notice that we have the Fourier support instead of physical supports. So on the left-hand side, this is this LP norm of the sum of those functions. And on the right-hand side, this is the little LQ norm of the capital LP norm of the functions fi. Because of this reason, an inequality of the form 1 is always called letter LQ, capital LP decoupling. And the fundamental problem of decoupling is to find the sharpest upper bound for the decoupling constant we have just defined. So it has a lot of applications in PDE, number theory, and geometric measure theory. For this talk, our focus will not be their applications, but the decoupling inequalities themselves. Before we move into the geometric details, I want to give some trivial estimates. And these estimates are called trivial because they hold for every family of geometric subsets. For example, the first thing is that most people are more interested in two extreme cases. One is when P is equal to Q is equal to 2, and when Q is equal to P. So these two extremes are called little L2 LP decoupling and little LP LP decoupling. They turn out to be the most useful cases in decoupling. And L2 is stronger by Hurter's inequality because we can always use Hurter's inequality to estimate the right-hand side. And the result is that the LP decoupling constant is always bounded about by the L2 decoupling constant times a cardinality factor, which is given by Hurter's inequality, but not vice versa. So in this sense, we sometimes say L2 is stronger. So that means if we can get a little L2 decoupling inequality, then it will automatically imply its corresponding version of little LP decoupling, but not vice versa. And next, so now we will come to the most trivial, or not the easiest case of the decoupling with some geometry. So in this case, we call it flat decoupling. Okay, so what do we mean? By flat decoupling, we are given a collection of subsets AI, I from 1 to n, and this n is a huge number. We let them to be congruent rectangles tiling a larger rectangle in R to the n. By some scaling invariance, you could always assume they are squares. It can be shown that the decoupling constant with respect to this family is comparable to the number to this power. And we know that this power is much larger than 1. Sorry, I mean n to this power is much larger than 1 unless both p and q are equal to 2. So this means that if AI is of this form, or more generally, if the delta neighborhoods of a manifold has some flat part, so in this sense, then the decoupling for that family of set AI is well understood. And this is not an interesting case we will study. So in general, we would like to avoid this flatness issue. That means we want at least some kind of curvature. For example, in the most important result in 2D, which is due to Bourgain-Demeter, we let AI be the delta neighborhoods of the graph of the standard parabola over a tiling of -1 to 1 into intervals of length delta to the power 1/2. So a picture looks like this. So the interesting part is that the function now is curved because the curvature of this function is a constant. And for this reason, each delta 1/2 by delta vertical neighborhood is roughly a rectangle of side length delta 1/2 times delta. This is the most important geometric observation so that decoupling would hold. And in 2015, their result is that for p between 2 and 6, the decoupling inequality for this p and q when q is equal to 2 is roughly 1 up to this epsilon loss. So the reason why we can get the decoupling roughly equal to 1 is because because of this curvature, we have some kind of destructive interference on the sum of fi's on the left-hand side of the decoupling inequality, while on the right-hand side, their sum is much larger. So the upper bound p equals to 6 is sharp, and actually 6 is the so-called critical exponent in 2D. For this talk, we will not be talking about why this is sharp, but focus on the endpoint case itself. And the reason we can focus on the endpoint case only is that by interpolation, it suffices to consider when p is equal to 6, but not other exponents. And as we just talked about, the geometric reason behind this partition of the unit squared, of the unit interval into side length of delta 1/2 is because the function x squared has roughly 1 positive curvature. So, and more algebraically, this is because the supremum, so this is because the difference of the function and its linear approximation at the center of I, which is this interval, is roughly equal to delta. And because of this reason, the length of I is nearly maximal. So by nearly, I mean up to some constant factor of this length. And here, maximality is very necessary for us to get an interesting decoupling inequality because we want to avoid flat decoupling. Because if the interval is much shorter than the maximum interval, then you expect a lot of this intervals, shorter intervals that are contained in a large interval. And this will result in the so-called flatness issue we talked about just now. Okay, so after we talk about the most fundamental case of Bourgain-Demeter, let's move on to one of my previous research. So in one of my last paper, I studied the so-called adapted partition for this decoupling for the cubic function. So suppose we are given a standard cubic function x cubed. Notice that the curvature of the function is roughly equal to x if we compute the double derivative. And this shows that when x is near 0, the curvature is very small. As a result, because we want this maximality condition to hold at least essentially up to a constant, we need to change the partition. So now we don't use the standard partition anymore, but we use the partition as this form. As you can see, when x gets closer to 0, because the curvature is smaller, we have to increase the length so that it's still a maximal. It's an interval of maximal length on which the function is delta flat. After we have done this modification of the partition, my last result is that we can still get the same decoupling inequality up to an epsilon loss. So the reason why we can choose this partition can be checked using the following Taylor expansion formula. So it's an easy exercise. So that is what I got previously, but now things get extremely more difficult in 3D. Let's talk about a fundamental result of Bourgain-Demeter. So they prove that given any phi, which has non-singular Hessian determinant, and this means that the graph of the function phi in 3D is curved. So it can be positively curved or it can be negatively curved, but it cannot have zero curvature. And if we let script A be a tiling of this unit square by squares of side length delta to the power 1/2, then the decoupling constant with respect to this family is roughly equal to the cardinality to the power 1/104. Notice that now we have this little L4, capital L4 decoupling. And actually, I think there's a typo here. So more precisely, it should be, okay, let me just roughly correct it. So this A is actually a tiling at the graph of phi over each square. So because we know we are in a 3D situation, so each AI is equal to the delta neighborhood of the graph of the phi over each square, not just the square in itself, of course, because we are in 3D. So after this modification, the little L4, capital L4 decoupling constant is bounded about by this number. And in general, we cannot obtain a little L2 decoupling because of some trivial issue. For example, as we can check that for the function phi xy given by x squared minus y squared, because this is a ruled surface, and for this reason, the delta neighborhood of the graph would contain a straight rectangle, and because we know that flat decoupling gives us the flat decoupling is not interesting, it gives a lower bound which is much greater than 1 for the decoupling constant. But in a convex case, we can still show that it's the decoupling constant is roughly 1. Oh, and then lastly, this 4 is the critical exponent in 3D. So we can recall that in 2D, the critical exponent was 6, but now in 3D, the critical exponent is 4. Okay, so that's the most fundamental result in 2D. And now what we discussed before was some more general polynomials. For example, like this case, phi of xy given by x cubed plus y cubed. So we know that the function phi has 0 Gaussian curvature on both the x-axis and the y-axis. Can we get roughly, so can we find an adapted partition A for which the same decoupling inequality holds as does Bourgain-Demeter decoupling? And the answer is yes. So there's a rough criterion for selecting this partition in this particular case. So we know that the function is given by the sum of 2 functions, one in x and the other in y. And for this reason, we can define a partition roughly to be the Cartesian product of the individual partitions in 2D. So we know that in 2D we chose this partition on the x-axis, and in this case it suffices to choose the same partition on the y-axis because of the symmetry. And this criterion is just a restatement of the 2D unit, the 2D 2D decoupling when we were making the partition. So we said this is just a rough criterion because for general polynomials, for general bivariate polynomials, it's much more complicated than this case. But as we know, in this very fundamental case, we can get roughly this picture. So we know that as x and y gets to 0, the rectangles become much larger, but as x and y gets to 1, it becomes roughly like delta to the power 1/2 times delta to the power 1/2. Okay, so finally, we can state our main theorem, which is the theorem about the decoupling for smooth surfaces. This is the main theorem of that we obtained. Let phi, which is defined from the unit squared to r, be a smooth function, and let delta be positive. Then, roughly speaking, there is a boundedly overlapping family. So for this moment, we can roughly think of it as a partition. So there's a partition strip A of rectangles covering the unit square, so that the following holds. The first item is that the delta neighborhood of the graph of phi over each AI is an almost 3D rectangle. We have just seen before in 2D that if we have chosen the correct partition, the correct adapted partition, then the delta neighborhood in 2D of the graph of each function phi over each interval is an almost 2D rectangle. But now, in general, in 3D, we have the graph above a rectangle is roughly a 3D rectangle. So this is just a generalization. And secondly, we have the following decoupling inequalities. So as again here, this is actually a typo, so it should be replaced by what we talked about just now. It should be the graph, the delta neighborhood, the graph of each AI, not just the sets AI themselves. After this modification, we have these two decoupling inequalities, which is the same as the Bourgain-Demeter decoupling up to this epsilon loss. So previously, this was a conjecture of Bourgain-Demeter camp, but now we have made them into a theorem. And what should also be noticed is that when they were stating this conjecture, they didn't talk about a convex case. But now it turns out that by a very standard technique of approximation, we can also prove the convex case when we can also prove this little L2 decoupling when phi is convex. So our result is slightly stronger. And another point is that when they were stating that this conjecture, they stated this for real analytic functions, but now we can do it slightly better to prove it for all smooth functions instead of real analytic functions. Okay, so for the remaining of the talk, let me just give a very brief sketch of the proof. So the first step is to use a Taylor approximation. So we fixed epsilon to be positive, so we know that we are allowed to lose an epsilon here. And given any epsilon, we just pick. We first tile this by delta to the power epsilon times delta to the power epsilon squares. Over each square, we approximate phi by its epsilon inverse degree Taylor polynomial with error to the order big O of delta. So notice that this function, this big O depends on the function itself, and it depends on a lot of norms of its derivative. So it suffices to prove the main theorem for all polynomials of degree D and coefficients roughly equal to 1 with the decoupling constant uniform in D. So what does that mean? We notice that we have tiled this by these tiny squares. Because we are allowed to lose an epsilon in the power, we just use triangle inequality and Hurder's inequality. And in this way, we lose a factor delta to the power minus epsilon. And then it suffices to prove it for each individual square. And for each individual square, because we are considering the delta neighborhoods, it suffices to decouple the function phi. It suffices to decouple its very high order Taylor polynomial. And the very important thing here is that the decoupling constant must be uniform. So it should be uniform in the polynomials. Oh, sorry. So more precisely, I think there's a typo here. So it should be uniform in the coefficient. So what I meant exactly was that the decoupling constant should depend on D only. So because as we know, each Taylor polynomial for each square should depend on delta. And if we cannot eliminate this dependence on delta, then the decoupling constant could also depend on delta, which is not what we want. We want the decoupling constant to be independent of delta, of course, but it is allowed to depend on epsilon, of course. And because D is only dependent on the function phi itself and epsilon, if the constant is uniform, it is dependent only on D, then the decoupling constant would only depend on delta. Sorry, the decoupling constant would only depend on epsilon and the function phi, but not on delta. So that's the key point. Okay, so in this way, we have transformed the decoupling of this function phi into a uniform decoupling inequality for bivariate polynomial. So this uniform is that the decoupling constant has to be uniform in the coefficients. And the very rough sketch for proof is as follows. It is by inductional scales, and it resembles the technique of one of my previous work, which was in 2D. But now it turns out that in 3D, with a much more detailed treatment, the same idea would also work. The first step is to write a large constant, which depends on epsilon and possibly phi only, to be determined. We construct partitions inductively at each scale, m to the power minus n. So that means, roughly speaking, how was this partition chosen? So at each step, we partition the unit square into the curved part and the flat part according to this inequality holds or not. So if the determinant is bounded above, then, sorry, if the determinant is small, which is the case here, then this will be called the flat part. If the determinant is at least this m to the inverse, then we call this a curved part. So for the curved part, we can apply Bourgain-Demeter decoupling, and this will give us the first term. So the proof of this somehow uses the standard result Bourgain-Demeter as a black box, but it should be noticed that we not only use their final results, but their proof, mainly the inductional scales technique, was also used in our paper. Not we didn't use them. You used the result completely as a black box. So for the curved part, after we have used Bourgain-Demeter decoupling, we get the first term. And for the flat part, we apply a very detailed and very subtle rescaling to this part. To the flat part, we can transform the decoupling of the function phi into the decoupling of the some scaled function phi, like phi tilde. And at that scale, we can apply induction hypothesis, because this is essentially what we meant by inductional scales. So because for the flat part, we can transform the problem of decoupling to a larger scale, we get the term on the right-hand side. So this means that using this rough idea, we can prove that the decoupling constant is bounded by the sum of two terms, the first term given by the curved part and the second term given by the flat part. And as in the previous slide, once we have proved this, we can we can iterate this inequality many times, so that the time of iteration, roughly speaking, is roughly log delta inverse over log m. So after we have applied the iteration this many times, we can get the final result. And this is how we get this is how we prove the main theorem of this decoupling for smooth functions. Okay, so lastly, you may ask why polynomials are important. Why do we use approximation by polynomials? We know that polynomials, first of all, has a lot of good algebraic properties, but most importantly, we have used extensively the following analytic property of polynomials. So given any polynomial, the supremum of the value of the polynomial over the unit square is comparable to the maximum of the absolute value of its coefficients. So we used this fact to help us in the rescaling within all those kind of arguments. So that's the very important point why we use polynomials. And also, in one of my previous papers, which is this 2D uniform decoupling, we can also invoke the main theorem in 2D to prove our main theorem in 3D. And that's another reason why we use polynomials. Okay, so I think that's the end of my talk. Thank you for listening to my talk.